We will start in a while. Okay, so we'll start. So last class we discussed all the assignment question of week 6. Week 6 was all about CNNs and its different blocks. Okay. In this class, we'll start with the week 7 assignments and we'll try to cover till week 8 since it is week 9. So rest we will try to cover subsequently as and when the uh, solution are released. Okay. So starting with week 7. In week 7, the question number 1 is, which among the following is a key feature of AlexNet? So as we know that do one thing. So this one for now. Yeah. So as we know, AlexNet is one of the first NN that is one of the first CNN that is proposed, and before that, LeNet was proposed, and AlexNet is sort of a basic CNN which was proposed in 2012, I guess, and it reached the state of the art accuracy at that time. So the question is, which among the following is a key features of AlexNet? First one is that it has 5 convolutional blocks. It is false. Second one is that, first one is it accepts input size of 1 into 24 into 20, 224 into 224. As you know, AlexNet is a CNN and it accepts, in the paper it was written that it accepts the input of dimension 3 into 224 plus 224. But in the actual implementation, they did 3 into 2. In the actual implementation, they did the 3 into 227 plus 227. So the input to the AlexNet is a RGB image with 3 color channels. But here they have written that it is 1 cross 224 plus 224. Hence, this is wrong. And option C is it has 5 fully connected layer. So fully connected layer is like this. It is the initial input layer, and this is the hidden layer, and every node from first layer is connected to every layer from second layer. So this was fully connected. That's what it is called, fully connected. Everything is connected to everything, and so on. But in CNN, not everything is fully connected. We have filters that we traverse the image with and give out another sort of extracted feature out of it. So no, it doesn't have 5 fully connected layer, but what it does have is that it has 5 convolutional blocks. Convolutional block is so convolutional layer is something that you see given an image. You have a convolutional filter and you apply it throughout the image, and you get another image. But the convolutional block is something we call if we combine convolutional plus ReLU plus pooling or something. You can club different things, but it will be called conpool, conpool ReLU or conReLU pool, like that. It's called convolutional block. So it has 5 convolutional blocks. Coming to the question number 2. Calculate the number of trainable parameters for the fully connected neural network with bias given as 2048, 512, 64, and 10. Right. So solving this question. So before solving this question, I would just try to give so how these things are calculated in general. Yeah. So let's say there is a neural network with input layer size of 4, hidden layer size of 3, and output layer size of 1. So if I connect everything of every node of this to every other node in the second layer and do the same for others as well. So there will be, for this, there will be 4. For this, there will be again 4. For this, there will be 4. Again, for this, there will be 3. And we have one associated bias with every nodes except the input node. So here it is 3 and it is 1. So total is 4 into 3 plus 3 plus 3 plus 1 equals to 12 plus 7 equals to 20. So what I did is that suppose suppose layer so this has like a sort of 3 middle layer or hidden layers, and the input layer is 4, right? And that's why what we did is that we did 4 plus 1, 5 into 3, that is 15. And similarly, 3 plus 1 into 1, 4. 64 plus 1. No, this method is not working. into 3. Okay. 3 plus 1 into 3 plus 1 into 1 is 4. It is 19. Is there a calculation mistake here? Like here, it is giving 4, 3, 3, 3, 3, 12, 12, 3, 16, 16, 3. Okay. 12, 3, 15, 15, 3, 18. 18 plus 1 equals to 19. It's not 21. It's 19. Yeah. So 15 plus 4 equals to 19. So what I did is that so here there is 4 layers, right? And if I multiply this with this layer, I'll get 4 into 3 equals to 4 into 3 equals to 12. But along with this 4, there is another bias coming along with this. So that's why I am adding 1 into 3 equals to 3. So instead of doing this 2 step, what I'm doing is that 4 plus 1 into 3. So when I'm evaluating for a layer, let's say L, I need to go for L minus 1. Sorry, I'm going for Li. I'll go for Li minus 1 subscript plus 1 into Li. Okay. So and I will iterate. I will sum it for all the layers. For layers for I equals to 0 to n for all the layers. I'll do this and I will have my answer. So for the given question, the number of trainable parameters for the fully contained neural network with biases given as okay. So I'll just write the values 2048, then 512, then 64, then 10. Okay. 204. So calculating for this, it will be 2048. I mean L minus 1 plus 1 into 512 plus the formula is I equals to 0 to n L I minus, so I equals to 1 to n L I minus 1 plus 1 into Li, lambda into Li, and here it will lambda of Li. Let's not keep lambda. Li, yes. This will give us, so I'll add it now with 64 plus 1 into 10. Sorry, it should be 512 plus 1 into 64 plus 64 plus 1 into 10. Okay, so I'll just calculate it. 2048, 2049 into 512, 104900. Let's just keep it aside. We add 5, 13, 513 into 64 plus 65 into 10. The answer is answer is 1082570. 1082570. Yeah, option C is the correct answer. So question number 3 is calculate the KB size in KB of the fully connected neural network without biases given below if the parameters are represented in a single precision. Okay. So it's the same network, I guess. Let me see. Okay. Single precision. So single precision number take around uh, one byte. So 1 byte is 8 bits. So 8 bits are needed for storing one trainable parameter. Since we have 1082570 number of parameters, so the number of bits that we need. Okay, no, we need 4 bytes. For single precision, we need 4 bytes. Yes, let me see. Four bytes. So you need 4 bytes. So total number of parameter is 10, 82, 570 into 4. And also we need to convert it to KB. So that we need to divide it by 1024. That will come around 1082570 into 4 divided by 1024 4228.78 4228.78 KB. Option A is the correct answer. Which of the following steps are used in convolutional autoencoder? So we discussed about autoencoder, and autoencoder was kind of center of discussion for quite a long time initially in this course. But since now we have developed methods for reading images, basically CNN. So we sort of now have designed convolutional autoencoder instead of designing vanilla autoencoder. So convolutional autoencoder looks something like this. If this is the image, if this is the image, and a convolutional filter will give me a like sort of filters around it, and I will build upon it. So one filter will give me one output, another will give me another output, and so on. So this is the basic setting of convolutional neural network. But convolutional convolutional autoencoder looks like is that from this we will do a fully connected layer. Fully connected layer, and that fully connected layer is then uncurtained to get an image, and from here we do deconvolution. In the deconvolution, we take an image and we deconvolve around it to get a bigger image like this. Like this. So the question is, which of the following steps are used in convolution autoencoder? Only convolution, only fully connected, and only deconvolution. So here we see that we have convolution, we have deconvolution, and we have fully connected. So I guess all of the above are used in an autoencoder. So yeah. Question number 5, which of the following techniques you can be used to implement deconvolution in a convolution autoencoder? The answer is convolution with fractional stride, because as you know, stride is something that when we have a convolutional filter, what you do is that we take that filter and parse it along the image to get a smaller version of the image. But when we do deconvolution and this convolution, when you do deconvolution, decon, so here is, and you can draw a smaller image. Here is the image, and we need to go from this to a bigger image, right? So what we do is that we like sort of traverse fractionally along the image and sort of cover things that are not there under this. And we sort of get a bigger image out of it. So fractional um, fractional convolution is something with stride is something. Convolution with fractional stride is something that we use for deconvolution in a convolution autoencoder. Give me 2 minutes. Hello. Coming to question number 6. Calculate the number of trainable parameters for the convolutional neural network given below. Input 1 into 32 cross 32. That is going to convolutional layer of 4C 5W 0P 1S. So let's decode it. So P means channel, I guess, and K means not sure about the notation that they have used here. 5 is the width and height of sort of padding is 0, that is evident, and stride is 1, so that is also evident. Padding 0, stride equals to 1, and number of channel input for the input layer is 1, and okay, the C is the number of filters then. So if the output is okay, so if the input is 1 cross 3 and 2 cross 2, we have this filters that is giving me that we have 4 filters that is giving me that is of size 5 cross 5, and we are using this to traverse the image of 1 cross 2 cross 2 with stride equals to 1 and padding goes to 0. Let's just draw it quickly. This is question number 6. These are very important questions. You need to know how to solve it. Okay. So here is a convolutional layer, and it is 32 cross 32. And so we have 4 filters. Filter number 1, filter number 2, filter number 3, and filter number 4. And each filter is 5 cross 5. Okay. And if it is and if each filter is 5 cross 5, and the padding here is 0, so we don't have anything around it, and the stride is 1. The stride is 1, and with this configuration, we know that what will be the output if I apply this. If I apply this, so in the output, the number of channels will be 4, because I will be getting 1 image for this, 1 image for this, and 1 image for this, and 1 image for this guy. So I'll be getting 4 output. But what is the dimension of this output? What is the height and width of this output? So height and width, the last class we learned, like we sort of derived a equation. Let's just look at that. Yeah, the equation was m minus w plus 2p by sw. So it was like let's say m minus w plus 2p by s plus 1, I guess. This was the formula. Yes. So the formula says it all, and it is so let's say this was width, and stride is also width. For height, we have minus height plus 2p height by s height plus 1. So this is 1. This is another. So here the height and m is 32, 32. Width and height of filter is 5 plus 5. Padding is 0, stride is 1. So let's just calculate what will be the output of it. The output will be 32 minus 5 plus 0 by 1 plus 1. So it will be 27 plus 1, 28. It will also be 28. So it will be 28. So this is output number 1. Yeah. So then just let's just calculate what is the number of parameters that we're getting from this layer at least. Yeah. So let's just look at the question again. Okay. So we have this input, we pass the convolution layer of convolution like this. And we are at this stage that what will be the output? So output size is 4 into 28 cross 28. So the number of parameters that we have here is let's say so what are the parameters? So last class we discussed that. So these are basically our parameters, right? These are our parameters. We sort of discussed that initially when deep learning started. Initially when the task of image classification started, we sort of looked at parameter. We sort of tried to handcraft these features. We say that okay, this feature gives me edges, and this feature gives me curves. This feature gives makes the picture blurry. This makes up, and we sort of took all these filters and we applied it on the images. And after applying it on the images, we got the corresponding transformation applied through that filter. But here what we did is that we sort of said, okay, I won't give you all these filters from myself. What I'll do is that I will define these filters as parameters, and your task as a CNN is that given a filter, given a task, you need to find those filters and optimize it in such a way that the learned filter will responsible for extracting all those meaningful and all those features that is essential for classification and or any underlying task. So the number of features, the number of parameters is something that we have in the number of that we have in the element of this filter. So here what we have, like we have 5 cross 5 and the number of channels is 1. So the number of filter we have is this channel into height, this 5 plus 5. Then we have one sort of bias associated with it. So the bias term will be there, like each one will have one bias. So we added 1, then into, we have 4 such filters, so into 4. So that will be 5. There will be 5 cross 5. 25 plus 1 equal to 26 into 4, 104. So 104 number of parameters that we have in the first layer. 104 first layer. Now the output of the first layer is 4 plus 28 plus 28, and we pass it to a ReLU layer. And as you know, ReLU doesn't affect the dimension of the input. Hence, we'll get 4 cross 28 cross 28. So the output is 4 plus 28 plus 28. And the number of parameter I have 0, because ReLU does not take any parameter into consideration. I will do it in the black. And also do it in the black. This is layer 1. This is layer 2. Let's see what next. Layer 3. Okay. Layer 3 is max pool. And max pool has, as you know, max pool, we apply max pool to every sort of channel. So if we have 4 channels, max pool will have, like, say, 1 channel and 1 cross n cross n, and we'll apply it to all the channels, like 4 channels here. So next is max pool 2W 2S 0P. So we had 4 cross 28 plus 28. We pass it to max pool, and the configuration is 2W. The configuration is 2W 2S 0P. I mean, the width is 2, stride is 2, and padding is 0. And we'll see what this looks like. Okay. So for max pool, we know that, like, the stride is 2. So the number of layers, the filters will be 4 as it is, because we're sort of doing it like this. We're sort of applying the same max pool filter for every for all the channels. So the number of layers will be 4, and yeah, so the number of layers will be 4, and since it is max pool, we'll calculate it like this. So the calculation will be similar, because so here it is 4 plus 28 plus 28. So let's just consider m as 28 and n as also 28. Since we're, like, sort of going irrespective of number of channels, the formula stays the same. 28 minus 2 plus 0. So let me rewrite the formula. It was m minus w plus 2p by p is pw sw plus 1 is equals to 28 minus 2 plus 0 by 2 plus 1. It will be 14. No, sorry, 30. 26 by 2 is 13 plus 1 equals to 4. And since m and n are identical, and all these things are identical, it will also 14 plus 14. So the number of parameters that you have here. So the number of parameters. So if you go to the internal working of max pool is something like we take the maximum out of it. So there is no parameters involved when we take the maximum. It's just only maximum, So we're just taking maximum value out of it. If you see the maximum function, it doesn't take any parameter. It just take the input, which was given from the previous layer of dimension 4 cross 28 cross 28. So number of parameters here is 0. So hence the output is 4 cross 14 cross 14, and the number of parameter is 0. In black. Okay. Coming back to the layer 4. Actually, all these questions are very intensive. If you nobody is here, but if someone is watching it later, you can solve this question and you will be able to solve other questions which are similar and sort of give similar flavor. And you will also develop insights into CNN and other architecture that has been proposed by different scientists in this domain. Okay. Coming to the next layer, which is again a convolutional layer of 8 filters, 7 cross 7 width, 0 padding, and 1 stride. Okay, so let me write that down. 4 cross 14 cross 14, and we're passing it to a one layer of 8C, 8 number of channels, 7 width, 0 P1S, 0 padding, and 1 stride. So by looking at here, I can say that the number of channels will be 8, because the number of channel must be 8, because as we need 8 channel in the output, we'll have 8 4 cross 7 cross 7 filters. So any filter that we do, like that we have in a layer L, I, will have same number of channel that will have same number of channel that was in the layer Li minus 1. So that's something we need to remember while designing SNM. So sort of going from here. So here M is 14 and N is 14. M equals to N equals to 14. And we shouldn't calculate the number of channels, because the number of channel that is expected in the next layer will be same. Okay, will be like that, 8 cross. So M cross N is 14. So let's just calculate the width and height very quick. Width and height will be 14 minus 7 plus 2 into 0 by 1 plus 1. It's 7 plus 1 equals to 8, and same will be for the width. It will be 8. The output will be 8 cross 8 cross 8. Okay. Now let's calculate the number of parameters that we got out of this. So we have channels here. So we have filters here of 7 cross 7, and each filter is sort of size. I just currently recently said that the filter size will be so the channel size will be same as the channel that is in the previous layer. So here it will be 4 then. Okay. So one filter is consisting of 7 cross 7 into 4, it is 196. Okay. And how many filters do we have? 8 filters. So 190. So 196 into 8 is equals to 196 into 8 is equals to so before going so 196, and we have also bias, one bias associated with it. 196 plus 1, and 196 plus 1, and multiply it with 8, because number of filters is 8, will be equals to 1576. So these are the number of parameters that we have here. Writing it similarly, we'll have 8 plus 8 plus 8, parameter is 1576. Okay, let's just go fast now. Layer number 5. Layer number 5. And layer number 5 is again a ReLU. So ReLU won't be changing anything. So ReLU will just take 8 plus 8 plus 8. ReLU will give 8 plus 8 plus 8. Okay. And the number of parameters, the output will be 8 plus 8 plus 8. Number of parameters will be 0. That's it. Going to layer number 6. Layer number 6, we'll have something. Layer number 6 is max pull. So 8 plus 8 plus 8. Max pull, and max pull has 2W, 2S, 1P, 2W, 2S, 1P. The output, we just need to calculate the output because it is also have the number of parameters. So calculate. We'll have 8. So number of channels will be 8, of course. And the input output will be 8 minus 2 plus 2 into 1 by 2 plus 1 is 8 minus 2 is 6 plus 2 is 8 by 2 is 4 plus 1 equals to 5. Finally 5 will be 8 plus 5 plus 5. 8 plus 5 plus 5, and the number of parameters. So the number of the output is 8 plus 5 plus 5, and the parameter is 0. We have a box here, and it's done. Layer number 7. The assignment is very easy, but it is very lengthy to calculate on this. With layer number 7, layer number 7 is layer number 7 is a flattening layer of 200 outputs. So we put 8 plus 5 plus 5 to a flattened layer, and we got 200 output. Here we won't be calculating anything. We'll be just calculating what this value is. 5 plus 5 is 25. 25. Sorry. So this is we're just flattening it. So flattening doesn't do any like sort of thing. So I'll just write it here. So just open up like me. and not a parameter set to 0. Have 200. Then we have a FC, and that FC is connected to 64, and then again the 64 is connected to output 10. I'll just calculate it the way we calculated earlier. So it would be 200 plus 1 into 64 plus 64 plus 1 into 10. It will be 200 to 1 into 64 plus 650. And it will be 12,864. 12,864 plus 650. That is equals to 404 5611 8 6 8 plus 6 is 14 15 31 3. So we have total 13,000 parameters here in this last two layer itself. Okay, so 10. Let's just add everything up. So total close to 13,514 plus 0 plus 0 plus 1576 plus 0 0.04. 104. And if we add all these things, we get 15,195, 94, 15,194. So this will be the output, I guess. If you add all these things, so the answer is C, correct answer. And next question is find the KB, like what is the KB that is used? I already solved a similar question in question number 5. So you guys try solving this while we'll take it a short 10 minutes break and we'll join after a few minutes. You just try to solve this in between. Hello. Hello. Yeah, I think my internet connection is unstable. Let me reshare the screen again. Yeah, I guess it's visible. Okay. Coming to question number 7. Calculate the size in KB of the convolutional neural network given below if the parameters are represented in double precision. And yeah, so the last question, we sort of saw that the parameters were represented in a single precision. Now we have this question number question number 7. Question number 7. So 7. So in the last question, we saw that the parameters were given in single precision. So for storing a single precision number, we have we need 4 byte for it. And here it is as if it is double precision. For double precision, we sort of need 8 byte of storage. And since we have 15,194 number of parameters, we need 1594 into 8, that will be equals to 4 into 8, 32. And let's just do one thing. 15,194. 15,194 into 8. 12, 15, 5, 2. 12, 15, 5, 2. It will be 12, 15, 5, 2. And since it is asking for us to give in KB, and if we divide it by 1024, the answer will be let me divide this by 1024, 118.70, 118.70, and the answer is B. Okay. Next question. Coming to the next question. Give me 1 second. Let me connect my earphone, reconnect my earphone to it. Give me 2 minutes. Fine. I hope it's audible right now. Yeah. So question number 8, find the dimension of output of the convolutional neural network given below. So let me write, so in the input dimension is 1 cross 32 cross 32. I'm audible, I guess. Yeah. Question number 8. Input dimension is 1 cross 32 cross 32. And we are passing these to a convolutional layer. The convolutional layer is 4C, 5W, 1P, 1S. And we're passing this to RLU and max pull of 2W, 2S, and 2P, then output. Okay. So starting with this, like we have the formula that if input image is of size M cross N and the number of channel is 4 and this is C here is 4 and size of filter is W cross W and padding is P and stride is S, and the output would be M minus W plus 2 into PW by SW plus 1, right? So this formula is derived in the last class. So if you want to follow along, you can go there. But if you are not, then just apply the formula. 32 minus 4, 5, W is 5, I guess. W is 5 and plus 2 into 1 by 1 plus 1. So this gives me 27 plus to 29 plus 1, 30. 30 and width will be 30. So the output of layer 1 would be 1 cross 32 cross 32. We applied count. We applied count and we got and it will be the number of filter that we have will depend on the number of channel that we're looking for. Number of channel here will be 4 and it will be 30 cross 30. And similarly, if we go for layer number 2, layer number 2 is a ReLU. It will remain the same. Layer number 3, layer number 2 will remain the same. Coming to layer number 3, okay. In the layer number 3, we have max pull of 2W, 2S, and 2P. So it will work like that. So 30 minus 2S, W is 2, is 2, P is 2, so 4, 2S, 2P, let me see. Max pull of 2S, 2 stride, 2 padding. So stride is also 2. Stride is also 2 and 2 plus 1. That will be 28 plus 4 is 32, by 2 is 16, by 2 is 16 plus 1 is 17. Okay. Similarly for width, it will be 17. The channel will remain the same of 4. So the output would be 4 cross 17 cross 17, like this. Option D is the correct answer. Coming to question number 9. Consider a convolutional kernel of size 5 cross 5 applied on an image input tensor X with stride of SW and SH and padding of PW and PS to the output tensor Y. Which of the following combination is true such that size of X and Y becomes the same? Okay, so let's just solve this. Question number 9. I have my input tensor X and I am applying a filter of size 5, adding a padding of size PW. Okay, let's just assume that everything is P, like same. So PW and height and width is same, square image. So to P by S plus 1 equals to Y. Since Y equals to X, we can write it here as X. That implies, and since, so this is like, so we want the output to be same as input. So output, if the output is Y, we want it to be same as X. So we can just write X in place of Y. So taking one to this side, X minus 5 plus 2P by S equals to X plus 1. That implies X minus 5 plus 2P equals to S into X plus 1. Okay. That implies X, and multiplying this would be Sx plus S. So if I just bring this to this side, it will be, if I just take this to that side, it would be, so let me just erase this. So in this side, it will be like, we just put everything into one side, Sx minus X plus S plus 5 minus 2P equals to 0. That implies X minus 1 plus S plus 5 minus 2P equals to 0. Okay. Let's just put the values that is there, that is given in the variables. S is 1 and P is 2. So if S is 1 and P is 2, so case 1, S equals to 1, P equals to 2. So if S equals to 1, we are doing this 0, there will be 0, P equals to 2, it will be 1. So it is not equal, getting equal. So 2 is S equals to 1, P equals to 1, I guess. Yeah. S equals to 1, P equals to 1. Okay, so S equals to 1, P equals to 2. Let me just check because they have said that it is the answer. And X, okay. So when, just check. So this will be 0, this will be 1, this will be 5 minus, this will be 5 minus 2 into 1, which is 5 minus 4 equals to 1. So did we do a calculation mistake here? Okay, this should be minus 1, not plus 1. Here it will be, it should be. Okay. It should be minus 1, minus 1. This is minus x. So here it should be minus x, not plus x, minus x. So here it is 1, here it will be minus 1 plus 1 equals to 0, which will be equal to this 0. Hence, LHS equal to RHS. So value of P is 2, sorry, value of P is 1, and value of P is 2 and stride is 1. And this is also same for the width and height, both in the horizontal and the vertical direction. And going to the next question, the last question, what are the different kernel size of convolutional layer present in VGG-A net? So VGG net only contains 3 cross 3. So you can check the lecture or the doubt, but this is this sort of effect. Okay, coming to week 8 questions, week 8 assignment questions. This is we should be completing this today, but let me see how far are you going. Which of the following CNN architecture has most number of parameters? The most number of parameter has of VGG16, because VGG16 contains only like 3 cross 3 sort of thing. So that's why okay. So that's why like the number of parameters that they are having in each layer is more. So yes, VGG16, you can just a factual question, you can just check. Then what is the range of activation after applying a local response normalization? Um, uh, okay. The range of activation after applying a local range normalization. Um, yeah, so local response normalization is a thing from GoogleNet. So in GoogleNet, we sort of saw that after applying local normalization, the output generally lie between 0 and 1. So that would be the correct answer, I would say. Question number 3, what are the different sizes of convolutional filter employed in inception blocks? So inception block is a part of inception net. So inception net, we sort of argued that instead of just using one dimension of feature, we can sort of model the different dimension of feature, and we for the same input layer and sort of get different output for different filters. And this is the idea behind inception net, and that we did. So the answer is D, 1 cross 1, 3 cross 3, and 5 cross 5. Question number 4. So this assignment is all factual. So last assignment was calculation heavy. This one is a bit factual. So you just have to go to the, lectures or so sort of see it in the internet to get. Google Net has dash layers, dash inception block, and content total dash number of parameter. This is a factual question. You can just check it. The answer is A. Question number 5, how many different sized convolutional filter are employed in GoogleNet? In GoogleNet, I guess uh, there are 4 type of different size of convolution filter employed in the GoogleNet. The answer says it, but yeah, do feel free to check it out. The fact the CNN architecture arranged in increasing order of total number of learnable parameter during training are. So basically, the learnable parameter during training sort of increases with um, the year they were developed, because with every year they sort of try to make the thing bigger. Okay, but here the correct sequence would be DNSNet 121, inception, P3, RESTNet, and VGG 16. VGG has like always has a highest number of parameters. Since RESTNet does skip connections is added, it doesn't have much number of parameters as VGG. Okay, and inception and DNSNet has lower number of parameters. Coming to question number 7, some CNN architecture employ 1x1 convolution filter layer at the beginning of each block, which are called bottleneck layers. Beginning of each block. Okay. The main objective of this 1x1 filter is to uh, uh, so this wish to. So option 1 is alleviate the vanishing gradient problem. No, I guess not, because there is no connection to vanishing gradient problem here. Reduces input feature channel dimensionally, thus minimizing the number of learnable parameters in the same. Yes, so if a filter is 1x1, the output will have same height and width, but the number of channel will be reduced. You can reduce the number of channel here. Okay. So if you just want to reduce the channel dimensions, and so that you will minimize the number of learnable parameters, then you can go for it. Encourages feature reuse. No, so answer is B, reduces input feature channel dimensionality, thus minimizing the number of learnable parameters in the same. Which of the following is a true for RESTnet architecture? Only avoid vanishing gradient problems, only encourages feature use, only contains skip connection. Answer is D, all of this, because so I just try to draw a RESTnet here to demonstrate. So RESTnet is something like if you have a layer here, right, and you have an output here, that output will be passed to the next block. That is fine. That is normal AIM stuff that is going on. But what they do is that they just also add this part. So what they're saying is that information at this point should not only depend for the information that is going through this, it also has to get some flavor of the past information. We should get the transform information and also past information. In this way, if this block is not necessary for a task, it won't be flowing much gradient through this. It will just use this path for gradient calculation and operation of weights. So this is the idea of RESTnet. So are they avoiding the vanishing gradient problem? Yes, because they're if the gradient here in this vanishes, still the gradient from this can go up to this and give some addition. Okay, and second is only encourages feature use. So feature use, like if the feature that is it is here, it will be reused again here, and without skipping this block. And only contains skip connection. This concept is called skip connection. This is skipping this entire block. So all of them are true. Then coming to the 9th question, the layer structure in blocks of RESTnet 101 and RESTnet 1669 are. I guess you just have to look in the answer for this, because these are very specific to architecture, and you shouldn't be remembering all the architecture and number of blocks. You should just go to the lecture and see what is the number of blocks there and just answer this question. Here the answer will be B, but yeah, that should be the way you should go about it. Question number 10, state whether the following statement is true or false. The input of each layer in a dense net block depends only on the immediately preceding layer. The answer is false, because in dense net, we sort of uh, take inputs from the, not from just from immediate output of the previous layer, we just take input from the prior layers. And this sort of a RESTnet sort of arrangement that is going on here. So this concludes our assignment 8.2. Okay, and I will be waiting for any other questions if anyone have, or if any doubts or anything. I will not be running code today because it's already time, and I think if we start doing the coding part now, we won't be able to finish it on time. So I'll just wait for 5 more minutes. If in case anyone joins, they can put their question on chat or just unmute themselves and speak. I'm muting myself and waiting till 6 to do this. And I would say that in the next week, in the week 10, assignment 9 and 10 solution will be discussed, because I believe till then week 10 solution would have been released. So I'll discuss that. And coming to week 9, we have space and complexity, computational complexity in DNN, domain adoption, transfer, turning, all these things. I'll give a brief overview of that. Activation, pooling, and rigid propositional network, unit, semantic segmentation, and all these things. This will have we'll cover in the next class. Let me see what is the number of weeks that is there that they are going to cover here. This is week 11. So week 11, adversarial autoencoders, adversarial autoencoders, classification, synthetic. So they're coming to generative modeling, and I will sort of have to go through it. Let me see what was the number of weeks that was there in the last year. I believe it must be week 12, right? The content are more or less same. Okay. So then I will leave up to it, and I will just leave you guys here and wait for others to join, or any questions if they have. I'll not try to start anything now. I'm just staying here. Okay, we'll end the session for today. Please no questions.